Hi, how's it going? My name is Carl Dees with the Learning and Research Center here at the University of Colorado, Denver. Today we're going to be talking about concepts associated with momentum. So let's get started here. Alright, so let's start with the overall idea of momentum because I think that can get a little blurry. And then bring it into the ideas of changes in momentum and what we're trying to say. So momentum, when we talk about momentum, when an object has momentum, we're just trying to describe a moving object, okay? Momentum is mv, that's what it is, not change in momentum. Change in momentum is something different, right? But momentum is mv, it's just an object that's moving. Velocity is moving, motion, right? And mass is the object, right? So momentum is just a moving object. That's just how we describe it. If an object's moving, we say it has momentum, right? And so that's the idea to think here when we're just talking about momentum. Why is that important to know? Because that's pretty straightforward, right? Well, the idea that we need to understand here is the difference between momentum and what the change in momentum is, right? The change in momentum, right? If we were to write the equation for it, the simple one, right, is the final momentum minus the initial momentum, right? Or another way to write it, right, would be, I'm going to write it up here, the change, this is not momentum, we'll do this here. And we'll say, another way to write the change in momentum, right, would be m1v final minus m1v1 initial, if it's one object. We're trying to describe the change in momentum for one object, right? So final minus initial, right? So we know there's two ways to write that. Let me write that a little bit bigger. Right, m1v final minus m1v initial. That's just the change in momentum for one object, right? So the change in momentum is the difference of two momenta, right? This is the initial momentum of the object. This is the final momentum of the object, right? There's two momentums in here giving us a change in momentum, right? It's the difference between changes in kinetic energy and kinetic energy, right? It's the differences between velocity and changes in velocity, okay? There's different things there, okay? So the changes are the difference between two values, where the instantaneous things, right, are just that one value. So changes in momentum are the difference between two momentum, right? So changes in momentum don't mean the same thing as just momentum. Changes in momentum is trying to describe the change in that motion's object, or the change in motion of that object, right? How the object experiences the change in motion, where momentum is just describing a moving object. Okay, so I'm going to get off of that, but that's what that means. It's important. It's important because it's how we kind of talk about momentum, right? We can talk about momentum in terms of, you know, just a moving object, or we can talk about momentum in terms of the change in momentum. Okay, both describing two different things. So, where's this idea coming from? Well, I think we described this in the energy video, but let's just describe it again. And we'll come back to this over here in a second. But force, right? Force is a small word to describe two things. If you apply a net force to something, which I just realized is not written here, but if you apply a net force to something, right, you're actually doing two things. You're actually transferring energy, and you're transferring momentum to that object. So we say, instead of every time saying, oh look, when I push on something, right, like this bottle, when I push on it, right, yeah, that's a force, but that's just the simple way to say I'm transferring momentum and energy to the object, right? There's potential energy for my hand, and it gives the bottle kinetic energy, right? There's also, my hand has momentum, and I transfer momentum to this bottle, that's why it moves. So force, even though we call force a force, force is actually this. It's a transfer of energy and transfer of momentum, right? So when things apply forces to themselves, right? Net force, right? When there's no net force, we know there's no transfer of energy and there's no transfer of momentum. But when there's a net force, right, we know that there's going to be transfers of momentum, right? We can have an idea, we can build up to that idea, right? So we know that Newton's second law describes changes in motion, right? Well, we know when we apply a force to something, a net force to something, we change its motion, right? or when we transfer momentum to an object, we change its motion, right? That's two ways of saying the same thing. And so that's what we try to start with here, is we try to look at, we use Newton's second law to try to come up with where is the change in momentum actually coming from, right? If an object experiences a change in momentum when I apply a net force to it, right? It has a change in motion. If I apply a net force, it speeds up, right? Where's that change in motion coming from? Believe it or not, Newton did not write his second law this way neither. He didn't start with it this way. He actually wrote his second law this way, where he said the net force is equal to the mass times the change in velocity over time, right? And then what he did is he looked at this equation and he said, m change in v. Well, that's the change in momentum there. I can solve this equation for the change in momentum, and I can see where the change in momentum is coming from. And that's exactly what he did. So he just brought t over because he knew that mv was a way to describe momentum. It was a moving object. And we knew that if v's changing, that must be a change in momentum. So we can solve this equation for the change in momentum, just that term right there, and we can see where it's coming from. So when he did that, when he brought t over, right, and multiplied t by f net, he saw where the change in momentum was coming from. It was coming from this thing that we call an impulse, right? So this force applied for a certain amount of time is what we call an impulse. And that impulse, if there's a net force applied for a certain amount of time, is going to give us a change in momentum. And that change in momentum can be a change in your speed, so you could speed up or slow down, or that change in momentum can be in terms of your mass, like a firework, right? A firework is one mass, and then it breaks up into three masses. That was a change in momentum for those. Those all experience a change in momentum because their mass, even if they were all going at the same velocity, there was a change in mass, so there was an impulse that caused that thing to explode, and so therefore there was a change in momentum as well. So we get an impulse. An impulse gives us a change in momentum. That change in momentum can either be a change in velocity or a change in mass, but that's what we see from Newton's second law, is where a change in momentum comes from, right? The next thing that we did is we said, well, Newton's third law is describing, right, what happens when I apply an impulse to something, right? I'm applying a force to something, or I'm essentially having a collision, right? So don't think collisions are just going to be two things bouncing off each other, striking each other. A collision is applying, like if I apply a force to something, that's a collision, right? I'm pushing on this bottle, but that's a collision. That's also an impulse. That's also just a force. I'm pushing on this bottle. I'm applying an impulse to this bottle, right? I can apply a longer force to that bottle, and that's more of an impulse, right? Versus that one. We can see that more of an impulse gives a more change in momentum or more change in motion for this object based off how much force and amount of time I apply it for, right? So we said, we looked at Newton's third law and said, hey, for any collision, we know that those forces are equal and opposite. Every time something, right, we apply a force to something, right? The force from that object into the other object is equal and opposite to the force that that object is applying back to me. So here, I apply a force to the bottle, that bottle's applying force back to me too. We know that from Newton's third law, okay? And the thing about Newton's third law is it's trying to do some things here. So that's what we say here, right? It says any collision, right? Force applied for any collision. Force applied to one object is equal and opposite to the force applied to the other. That's the first thing we say, right, for Newton's third law for any equation, right? It also implies, the third law also implies that during a collision, both objects experience the same impulse, and each object transfers momentum to each other. So it's indicating both of these, that each object experiences the same impulse. If they're experiencing the same impulse, that means they're experiencing the same changes in momentum, okay? And that's telling us that there must be a transfer of momentum to each object, especially, right, if one object's sitting still and another object runs into it and they both start to move, well, why is that object moving? Yeah, the forces were equal, but it must have also transferred some of the motion into that object. How do we know? Because that's what happens during a collision, and that's what Newton's third law is trying to imply, okay? So we use Newton's third law, right? And kind of look, right? Start with Newton's third law and say for any, like, this is Newton's third law, but it's also describing a collision, right? Where the force from the first object to the second object is equal and opposite to the force from the second object back to the first, right? So this equation is describing two colliding objects, right? Newton's third law describes two colliding objects, right? And what it also indicates, right, from this is that if the force is the same, then the impulse must be the same, right? The impulse from the first object to the second object is going to be equal and opposite to the impulse from that object back to the other one, right? So the impulse I put into this bottle is the same impulse that bottle puts back into my hand when I apply force to it. That's what Newton's third law can indicate, because if the force is the same, then the time spent during that collision can't be any different. How does one object spend more time with another object than that object spends with the other, right? That's impossible. So we know that when they collide, they experience the same force, and they experience that same force for the same amount of time. Okay, so we know that Newton's third law indicates that they experience the same impulse, and if they experience the same impulse, right? Impulse is equal to change in momentum. If the impulse is the same, that means the changes in momentum are the same, right? And it doesn't matter the size of the objects. It doesn't say anything that in here. And we knew that from Newton's third law. If you don't remember, go watch the Newton third law concept video. Because we said you could have a 300-pound boulder and a 2-pound boulder. When they crash into each other, when they crash into each other, the force from the boulder is the same amount of force from the boulder is being put into the small boulder as the same amount of force from the small boulder is being put into the large boulder, right? They apply equal force to each other when they collide, even though the boulder's the 300-pound boulder is way larger than the 2-pound boulder, right? That's what's super important here to understand, okay? Is that even though, right, those one object's larger than the other, they still apply the same force to each other. So if I have a very large object and it collides with a very small one, what we're saying is that those forces are equal and opposite between those two. The forces are equal and opposite between those two, and the impulses are the same. So if I have a 200-pound box and a 1-pound box and they collide, the forces are the same between them because the size don't matter. The forces are the same, the impulse is the same between them, and if the impulse is the same, the changes in momentum are the same between them, right? And how are they equal? Because we know the changes in momentum, right, are equal to mv, right? Or m change in v or change in mv, right? Here we're just looking at the change in motion. We're trying to just look at two colliding objects, not a separating object, right? So we can see, right, that they're equal to each other, but how can that be true for large objects? This is how it's true, right? If the small object has a small mass, right, when it collides with the boulder, it's going to experience the same force, so it's going to get a larger velocity, right, after the collision than the larger mass is, right? The larger mass is going to experience a smaller velocity. So when you end up putting the numbers in here, they end up being the same, right? It's like if the boulder was 2 kilograms, right? And it was moving at 5 meters per second, and the other boulder was 5 kilograms, but was moving at 2 meters per second, right? This is a larger boulder, 5 kilograms, right? But it's moving slower, 2 meters per second. This is a smaller boulder, 2 kilograms, but it's moving faster, 5 meters per second, right? Well, we know 2 times 5 is 10, so on this side, the change in momentum is equal to 10. On this side, the change in momentum is equal to 10, right? But the numbers aren't the same. This is 5 kilograms, right? This is 2 meters per second, right? The larger object's moving slower. Where over here, the smaller object, the 2 kilogram object, right, is moving faster, right? So even though the numbers aren't quite the same, here they are quite the same, right? But the masses are different, right? We still end up getting the same numbers, so they end up being equal, right? That's just an example of how that works, right? But this is the equation that we're looking at, okay? So we can see by using Newton's second law and using Newton's third law that the changes in momentum when two objects collide will be equal and opposite. That is important to know, all right? Why is that important to know? Because of conservation of momentum, okay? With conservation of momentum, we're saying some things, right? We're trying to talk about when momentum is being conserved. So we've talked about when energy is conserved, right? Remember when energy is conserved? You know when energy is conserved, right? So it's when the total energy is equal to 0. That's how we know when energy is conserved. When there's no non-conservative forces. Energy is conserved, we could write it over here, right? When the change in E is equal to 0. That's a good way to write it. When the change in E is equal to 0, just like we know that momentum is conserved when the change in momentum is equal to 0, right? So we knew energy was conserved when the change in energy was equal to 0, where there were no non-conservative forces. Right? And we can say the same thing about momentum. Momentum is totally conserved, right? The initial momentum and the final momentum will be equal to themselves, just like we said the initial energy and the final energy will be equal to themselves for the conservation of energy when the external net force on the system is 0. But that's a weird thing to say, right? So another way to say that is that there's no non-conservative forces. There's no friction, there's no drag, there's nothing like that, right, during the collision. So like, if two cars are moving really fast and they collide into each other, the cars heat up, not from the engines, but because of the friction of the metal, right? So that the momentum isn't totally conserved in those situations because there's some non-conservative forces. The net external force, right? That external force there would be the friction, right? Isn't 0. There's some friction. There's some external force there, friction. There's heat being lost, right? So therefore, the momentum isn't totally conserved. But what we say in this class, we don't get into tricky situations in algebra-based physics class. So what we say is momentum is always conserved for closed systems. We're just assuming that all systems, and that's what we said for energy, right? Energy is always conserved for closed systems as well. We're just going to assume that every system we're talking about in here is either closed or that net external force is negligible. Like if we do talk about two cars crashing into each other, we're going to assume that the friction there is negligible, or we're not going to worry about it. But keep in mind that momentum isn't always conserved, right? Just like energy wasn't always conserved sometimes. But in this case, for this class, we're going to always say that it will be. Okay, so understand that it's not, but understand why we're saying that it is in this class. So, for conservation of momentum, like we said, the change in momentum is equal to the total change in momentum for the system will be equal to 0, or the initial momentum will be equal to the final momentum. That's what conservation of momentum is saying, right? And so another way to build, or the way that we build, sorry, not another way, the way we build this equation, the conservation of momentum equation, is we look at the collision between two objects, right? Which is what we were doing down here. And we say, okay, the change in momentum for the first object will be equal and opposite to the change in momentum of the second object. And then we expand those out, right? Kind of like we did here, but we make it a little bit further, where the change in momentum for the first object, right? This is the change in momentum for object 1. This is the change in momentum for object 2. So the change is the final minus initial, right? So here, this is m1 v1 final minus m1 v1 initial, because that's the change in momentum for object 1. Again, we're trying to come up to derive this conservation of energy, this conservation of momentum equation from two colliding objects. So when two objects collide, right, they're going to have an initial velocity and final velocity. So this is the initial and final velocity of the change in momentum for the first object. This is the change in momentum for the second object, m2v2 final minus m2v2 initial. Then what we do is we want to look at how the initial momentum, right, because we said the initial momentum should be equal to the final for conservation of momentum. So what we do is we rearrange this equation because we have final over here, initial here. We want our initials together, right, and we want our finals together. I just noticed that this equation, there we go, wasn't quite written, right? Let me write this better. M1 initial. There we go. This has a negative sign in front of it. If you're wondering what I'm doing, I didn't put the negative sign in front of this. So these need to change signs, right? Since this is negative, this side needs to change signs. You need to know this, okay? You're typically not given these equations on your equation sheet, so you have to derive them. So I want to make sure this is So this side, there's no negative sign, it's signed with the change in momentum, so it's just final minus initial. But this one, there's a negative sign associated with the change in momentum, so it changes the sign, right? Here we know it's final minus initial, but if there's a negative sign over here, this would be negative and this would be positive, right? But it's not, because there's no negative sign over here. But since this one has a negative, this one turns negative, this one turns positive. And then what we do is we bring the initials together and the finals together. So this final adds over, this initial adds over, and we get the initial momentum on one side, the final momentum on one side. And this is right here, I tell you, is how we're comparing the initial momentum and the final momentum, but it's also the conservation of energy equation, okay? This is a very, very important equation. It's describing the initial momentum and the final momentum of two colliding objects, okay? All right, so what's important here to understand? Oh, I just realized looking at this that I forgot to describe something over here, so let's describe something real quick. So we can look, there's this little note right here that I should have taken note to then, and I apologize. But we have to realize that unlike energy we just got done with, which is a vector, which is a scalar quantity, we are now dealing with vector values for momentum. Momentum is a vector again. So that means we can do some stuff, right? That vector means something, right? So when we're looking at impulse, right, the vector of change in momentum, so when you get the total vector for the change in momentum, you're actually indicating the impulse or how much force during the collision. So you can have two objects, right? You can have a ball that's gonna, let me do that down here. So you can have a ball, actually this might be a better place, sorry. Right, this ball's headed this way and this is a sticky ball, right? And then we have the same situation. So this is like a bowling pin here, and this ball's gonna hit that bowling pin, but this is a bouncy, okay? They both have the same initial velocity and both balls have the same mass. But for the sticky, there's not gonna be any final velocity, but for the bouncy, we're gonna have a final velocity, right? So when we do the change in momentum, which is final minus initial, we use the vector, right? We use the vector, the velocity vectors to get the change in momentum, right? I'm just going to use the tail-to-tail method here. This is VF, this is VI, and we draw, right, the net vector from the tip of the vector with the subtraction sign in front of it to the tip of the vector without the subtraction sign on it. So we see for the bouncy ball, that is the, yes, it's the change in velocity vector, but it's a change in momentum vector. Meanwhile, for the sticky, right, the change in momentum is just going to be, right, mv final minus, change in momentum is going to be mv final minus mv initial, but what do we know? It has no mv final, the sticky. This is going to be 0. So we know that the change in momentum for this is just the negative mvi, or the initial momentum, which means that we just reverse this vector. So that is, yes, it's the initial velocity, but it's also the change in momentum. So we can see that this change in momentum vector is much larger than this one, meaning that this ball experienced a larger impulse. That's what this means. We can get those vectors. Those vectors mean something. We can get the vector for the change and see what the impulse is doing. Okay? That's what that's telling us. Okay, let me make sure that that's clear because there's a lot of stuff over here. And I do this again in a separate video, this. And I want you to understand what I'm saying. So you can get the change in momentum vector. It's going to tell you how much force was in the collision or what impulse was there. Another reason, right, or the strength of the impulse. Another reason why it's important to understand that these are vector values is because once you get this conservation of momentum equation, you need to know that the signs will change, right? If I have two balls coming towards each other, right, that's their initial velocities, and then they bounce off each other, there's their final velocities, right? We know that they're going to have different signs because these velocities are vectors, right? So we know that the initial velocity for this one is going to be positive, but we know the initial velocity for this ball is going to be negative because of the way it's pointing, right? And then the final velocity for this ball is pointing negative, and the final velocity for this ball, right, is pointing positive. So we know this is going to be positive, right? So these are the signs. You can see that. These are the signs. Is that making sense? These balls are coming together and then they're going to bounce apart, right? These are the same balls. These balls are coming together and then they bounce apart. So their signs come from the direction that the vector is pointing. This is negative because it's pointing negative. This is positive because it's pointing positive. Okay? Super crucial to understand. So that means when you write this equation, this V initial, right, it's going to be positive, but this V initial, this needs to be negative in here when you go to write the equation for this situation, right? And I'll do it. M1 V1 initial, then minus, this is V initial minus this M2, this is M2, this is M1, right? M2 has a negative initial velocity, so we write M2 V initial as a negative sign. And then here, the final velocity of M1 is going to be negative, so negative M1 VF plus, because now the M2 is going to have a positive velocity, M2 VF, right? So see how even though I'm using the conservation of momentum equation to describe this collision, the signs can change in there, okay? So just be ready for that. That's what's important to know, and you got to pay attention because the signs will change in this equation based off the direction of the vector, okay? And again, we don't give you this equation typically on the equation sheet, so make sure you know how to derive it. Now, there are different types of collisions. This is real easy to get through here, so don't it looks like a lot more than it actually is, but there's 3 types of collisions that we got to worry about because that's what momentum is really trying to describe for us. So the first type of collision is an elastic collision, okay? And that's when momentum and kinetic energy are totally conserved, all right? It's only going to be bouncy situation. So this is this equation is describing two objects bouncing off each other. So this is the momentum equation you're going to use for elastic collisions when momentum and kinetic energy are conserved. And this is the kinetic energy equation that you'd use for it. All right? This is typically used for 2-dimensional objects. Okay? Because like I said, most of the time, momentum may be conserved. I might not have said this, but most of the time what we're going to see down here is momentum may be conserved, but energy might not totally be conserved. There might be some friction or something, right? So this elastic one is when kinetic energy, the initial kinetic energy and the final kinetic energy are equal for the objects, right? And the momentum, right? The initial momentum, final momentum are equal. That's what an elastic collision it is, and it's typically bouncy. All right? That's like if you were to let go of a ball and it bounced and it came right back to your hand. Balls don't do that, right? If you let go of a ball, it bounced. It might come really close to coming back to your hand, but it might not. It typically doesn't make it all the way because it loses energy when it hits the ground. But if it didn't lose any energy, it would come right back to your hand, and that's what we would call an elastic collision. All right. So then, what's an inelastic collision? Well, an inelastic collision is when only momentum is conserved, not kinetic energy, okay? Only when momentum is conserved. Make sure you can see these as well, right? So inelastic collision is only when momentum is conserved, not kinetic energy. So we only can use these momentum equations to describe the collision. That's what we mean up here too. It's like we can use kinetic energy and momentum to describe the collision for an elastic collision, but for inelastic, we can only use momentum, right? So for a bouncy situation, this is your equation. Make sure that you know these, because like I said, you have to derive these. They're never given to you on your equation sheet. So this is the equation for a bouncy. 2 objects bouncing off each other, right? They're going to have initial velocities and final velocities, the 2 objects, right? This is the equation for when 2 objects stick together. So initially they're going to have 2 separate momentums, right? This is going to have a momentum and this is going to have a momentum. They're moving together, then they hit and they move, they stick together and move together. So after the collision, they're going to have 1 velocity and their masses will be added, right? So this is a sticky situation that is considered inelastic. And then you can have separation, right? Where everything can be one mass, one velocity, initial velocity, and then after the separation, everything has its own mass, every piece has its own velocity, okay? So this is the equation for separation, when objects separate. All right, so make sure you know all three, because like I said, you have to derive these on your own, or you can just memorize these, but this is bouncy, this is sticky, this is separation, okay? Now for total inelastic, that's only when objects stick together. Inelastic collisions can be bouncy, sticky, separation. But for total inelastic, that's only when objects stick together and stay stuck together. Because I can have two things that stick together and then eventually they separate again. But this is when objects stick together and they stay together and then they come to a rest and stop and stay stuck. That's what we call a total inelastic collision. Okay? And that's really, again, since that's a situation, we can really only use the sticky equation, right? Which is we have two separate momentum at the beginning, and then we come together and stick together and move, so final velocity with the masses together, okay? So, that's momentum, right? Let's just review everything, because energy and momentum go together, and you gotta use them together, and you gotta know how to use them together, right? So we already said that force is actually just a transfer of energy and transfer of momentum. You need to know that. Okay? When you go to use these together, energy will be used to describe the motion of the objects, the two objects before the collision or after the collision, okay? So energy is only used, you're going to use the transfer of energy, these equations, right? These types of equations, right? Or there's one more. Maybe instead of writing this one, I should write K initial plus U initial, because this is really the one you should have here. K final plus U final, right? So to describe the motion of an object before and after a collision, you can look at the amount of work done and the change in energy, right? This is for non-conservative forces, if there's friction or something. But if there's no friction and energy is totally conserved, then you can use this equation to describe the motion of the object before and after the collision, okay? But if you got to describe the collision, you got to use momentum. Okay, so momentum describes the collisions, what happens when they hit. Energy doesn't do that, momentum does. It can, but when you use these together, you want to use energy to describe the motion before or after the collision, and you want to use momentum to describe the actual collision. Okay, and so when you do that, right, you can look at the impulse and see how it changes momentum, or you can look at the conservation of momentum. Right? Both of these are going to describe the collision, right? So don't forget that energy is a scalar value, momentum's a vector value. Okay? When momentum's totally conserved, the change in momentum is zero. When the energy is conserved, the total change in energy is conserved. Okay? Or the total energy is equal to zero. That's when the energy is conserved. Okay, so don't forget those. That was a little review. But that's also how you use momentum and energy together, all right? Okay, well, I hope this was helpful. Remember to go back, rewind, watch things over and over again, because that's what a video's for, not to watch one time. All right, I'm super proud of you. See you on the next video.